translational invariance among the space-time symmetries of the action. We only did with space-time translational invariance. But there's also another symmetry on space-time which we have used, but we have not discussed what the Noether conservation laws are related to that symmetry. So that's an open question. There were some confusions when apparently he tried to read Newton's textbook. So today we shall look into that. But before that, I'd like to do something which I feel is important. So let me start the presentation. Okay, so is there anyone who cannot see the screen right now? Is the screen okay now? Is the screen visible? Hello?
Yes, sir.
Screen is visible, right? Okay, so one of the things we found was that a complex scalar field, when coupled to electromagnetism, had a fairly simple looking action, a Lagrangian, which looked like this. dA phi. Phi is a complex scalar field times dA phi bar. Bar meaning complex conjugate. And then we have the potential term, which is mod phi squared. And then, of course, we had the Maxwell term.
Sir, one small clarification.
Yes, please, go ahead.
Sir, the previous class, what we did, the main objective was to make U1 symmetry local, no?
No, the main objective was to make the vector potential interact with the charge.
Okay.
Because we want to use the vector potential as a probe. You know, the vector potential is an electromagnetic vector potential. So if it can be made to interact with the charge, then we know that the charge is an electric charge. If we couldn't make it interact with the electric charge, then we would say, no, this is not the electric charge. It cannot be used as a model of electric charge. Okay, so the whole idea was that, and when doing that, when introducing the simplest form of the coupling via the Noether prescription, we found that the resultant theory, the interacting theory, automatically displayed local gauge invariance. Okay,
so
another way of saying it would be that if electromagnetism has to couple to charge, it must be locally gauge invariant. Okay, now so there's another way of doing the whole thing, which is a textbook way. I should tell you perhaps a textbook way. See, we derive this action from Noether coupling, right? We coupled the current, the Noether current, corresponding to U1 global symmetry to the 4-vector potential. That's what we did. Okay, but you could do it another way. So since you've asked the question, maybe it's good to do it. So you begin not from this, but from this, from the action, which looks like this. Without electromagnetism, right? So you begin with this action. Okay, and then you realize that, of course, this is global. By global, I mean the parameter of the U1 symmetry is independent of space-time. And the current is the same as before. JA is I, phi, del A, phi, psi, phi bar, etc. Right? That was our first lecture on this Lagrange density. Remember that? So this has global U1 symmetry, which means that phi goes to some phi tilde equal to e to the I omega phi, where this omega is space-time independent. Okay, so now insist on writing down L such that L is symmetric, or I should say invariant under local U1 transformations. So what is a local U1 transformation? Well, a local U1 transformation means that it is the same transformation with omega is equal to omega of x. Now, if I insist on this, then I immediately realize that that's not possible, because del A, see, under the global transformation, this transforms del A phi transforms as e to the I del A e to the I omega del A phi, right? And this transforms as e to the minus I omega del A phi. So e to the I omega and e to the minus I omega cancel each other out, and therefore you have the global symmetry. But when you have local, suppose you now make a local transmission, you find that this becomes, which is equal to del A phi plus I del A omega phi. And similarly for del A phi bar, right, with a minus sign here. So that's the change that occurs if you insist on writing down something which has this invariance. So obviously this won't work because the Lagrangian is not invariant. So what do? We define, we define a new derivative, and that is called a gauge covariant derivative, which is dA phi, which is defined as partial phi minus I AA phi, where AA is a vector potential. 4 vector potential. And you can say that it is the 4 vector potential of electrodynamics. Okay, so when you do this, what you find is that dA phi tilde, and this we derived yesterday, so I'm not going to derive it again. This is e to the I omega dA phi. You see, this is a great point, that when you change the derivative to the gauge covariant derivative, the gauge covariant derivative transforms under a local omega exactly as the ordinary derivative of phi transformed under the global omega. So then, well, once we have this, we realize that dA phi tilde dA phi bar tilde is equal to dA phi bar. So that is gauge invariant. Then this combination is gauge invariant, which is why this combination is gauge invariant. And if you identify A with the vector potential, then of course this invariance comes if you impose AA goes to under omega of x goes to AA tilde is equal to AA plus LA, which is a standard U1 gauge transformation of the vector potential. Oops. Local U1 gauge transmission, that's what I meant to say. So this way, this way of doing it is a standard textbook way of doing it, and there's a name for it. It's called the minimal coupling prescription. So in the minimal coupling prescription, what you do is you define covariant derivatives which transform covariantly, and that means that they transform exactly like the field phi under the local U1 transmission. So the reason of doing this is because when you do this, you find this combination is gauge invariant, and therefore it can be part of the action. Okay, so this is called the minimal coupling prescription. Now, the reason I didn't want to do this is because here this definition comes out of the hat. So the minimal coupling prescription is a kind of prescription. Now, I always associate prescriptions with doctors. Doctors give prescriptions. Scientists, especially theoretical physicists, derive results. So I felt that, well, we already had a prescription from Noether. Okay, the Noether coupling prescription was already there. So could we not use it to derive the gauge invariance? And that's what we did. Okay, but it's like a matter of taste. See, most textbooks follow this minimal coupling prescription. So if you followed the minimal coupling prescription, you'll be very popular. You'll be with the crowd, okay? Because most people are doing that. But then some of us prefer not to go the way most people are doing. We prefer to do things our way. And also, it's kind of fun to explore alternative routes to what most textbooks are following. Okay, this is always fun, and I would encourage you to do that. I mean, alternative routes could also be alternative to Partha Majumdar's lectures. Okay, even that is very desirable. So if you find something, some new way, nice way of doing it, I mean, it has happened. It has happened, I think, 3 years ago. 3 years ago, when I was teaching this course in this master's class, there was a student called Zahid, okay, and on a problem regarding radiation, I was trying to derive some result, and I was making things very complicated. When he piped up and he said, "Look, I think you're doing things in a very complicated way. Why not do this?" And believe it or not, we actually developed that. Sahid, another student from Presidency, and I have written a paper. It's on the archives. You can see it. It's not published for reasons unknown to me. I have not heard from the journal for 6 months, so I have to submit it to the journal. But it's a paper on electrodynamics, and you can see it on the archives. Okay? So, and Zahid was a student at ICS, an MSc student, when we did that work. So I would strongly encourage you to find alternatives to what I'm doing if you can. If you can, without wasting too much time and without, and making sure that it's really an alternative. Okay? But otherwise, you're strongly encouraged to do things your way. Okay? That's always very strongly encouraged. Right. So now, okay. So Akshay, I hope this minimal coupling prescription.
Yes, sir. Yes, sir. Yes, sir.
Is yeah, right. It rounds off the story.
Yes,
But one more thing before I finish it is something I don't know. I would call it the Ricci identity. Although the identity by Ricci actually shows up in GR, in general relativity. There's an analog of this in. Let me just put an inverted comma, Ricci identity. It's kind of a very cute result, and it's actually geometrical. So since I'm on this issue of covariant derivatives, suppose you look at this point. That is to say, commutator of two covariant derivatives. Now, if this were ordinary partial derivatives, that would be zero, right? Obviously. But because you have the A field in the definition of the covariant derivative, this in fact is not zero. So maybe I should maybe I should allow you to play with it, and you can prove that this is actually minus I FAB phi for complex phi. The phi that we've been talking about. That is. So let this be an exercise. Okay, I'll put it in as an exercise, and yeah, it's a few lines exercise, 3 or 4 lines, and I think it was fun doing it. Now,
sir, it's a commutator bracket or it's Poisson bracket?
No, this is a commutator bracket.
Okay, fine.
So what I mean is you calculate first dB phi and then do dA of that and then reverse A and B so that you have the antisymmetric combination. So this is a commutator, not a Poisson bracket. Okay, which is to show that a commutator, although Dirac was the one who brought in commutators of dynamical variables in quantum mechanics as sort of a generalization from Poisson bracket, commutators, this kind of a thing has been known to mathematicians. They're actually called Lie brackets in mathematics. So they've been known to mathematicians much earlier than much prior to Dirac. And some people say that Dirac did a special program in mathematics where he learned all these things and then brought them over to physics. So I don't know if that is true, but it may be that Dirac knew all about the Lie bracket and simply realized that the Lie bracket would be a lovely way of doing things, doing quantum mechanics, if you then make an association of the Lie bracket with the Poisson bracket. So the Lie bracket occurs in the theory of Lie groups and Lie algebras, of course invented by Lie, Sophus Lie, German mathematician. And so it was known, and it is this one which Ricci came long before Dirac. Ricci was 19th century, and so this is called the Ricci identity. So what is the interpretation? The interpretation here is a bit peculiar. So it's kind of a geometrical thing. I mean, remember that when we spoke about one way of wondering about the vector potential, we spoke about this space-time, and at every point there is a kind of jharu stick going on. Remember that? So this space of jharu sticks is called, it's not space-time. Space-time is right here. So at every point in space-time there's a stick like that, and this is called a space of fibers. And that's a fair enough word because these do look like fibers, and this is therefore a space. Now in this space, this Ricci identity tells you that FAP plays the role of curvature. Okay, so the fiber space, the space-time does not have curvature because this is Minkowski space, it's flat space-time. But the space of fibers does have a curvature. And the curvature is nothing but our FAB, our electromagnetic field strength tensor. Okay, so this is the whole point. I mean, this, in GR, when some of you will go on to do GR, you'll find that there is an exactly similar identity where now this will be replaced by space-time curvature. But here, there is no space-time curvature because space-time is flat, but there is another space, the space of fibers. And in that space, there is curvature. And the curvature is nothing but the field strength tensor. Okay, so this is some nice mathematical property, which so for those of you who are mathematically minded, okay, so another way of thinking about it is that dA dB phi, you see what each of these does, dA, is like pushing, so it's like pushing on the space of curvature, pushing along the fiber. Okay, that's what dA does. So this kind of a thing is like, see, when you calculate curvature, any kind of curvature in any space, you always have to consider this kind of a quantity where you push along one direction and then you push along the other direction, and then again you come back to the starting point and push along the second direction. So you go like this, or you go like this and like this. And when you do that, if you do that to any vector, of course here the phi is a vector in the curvature space. It's not a scalar, it's a scalar in space-time, but it's a vector because when you do a gauge transmission, it moves, right? Phi moves. So you see, when you move along this and you move along this, any vector will undergo a change. And that change is what is captured by this curvature. Okay? Anyway, I don't want you to take too much of your time on this, because this can go on and on. This is a beautiful subject, but I just wanted to give you a glimpse of so much that you can derive within electromagnetism, okay, which has this geometrical significance. Okay, so now we go to Raj's question, right? And so we leave this gauging variance business and we go to Raj's question about Lorentz invariance. So Lorentz symmetry. Well, I think all of you remember, because we have hammered it home, that there is this Lorentz transformation. So a Lorentz invariance is defined by, a 4-column vector x going to some 4-column vector x tilde, which is equal to lambda x. Or if you write it with indices, then it's just this, right? So this is something we all know. And we also know that this leaves ds squared invariant if and only if lambda eta lambda is equal to eta, with eta being diagonal 1 minus 1 minus 1 minus 1. That means it's a diagonal matrix with these diagonal entries. Okay. So we know this, and that's where we begin from. That's what we mean by a Lorentz transformation. And we know that lambda has in it Lorentz boosts as well as spatial rotations, right? Now let us look at infinitesimal Lorentz transformations. That means that our lambda must be equal to some identity plus, let's say, a small lambda. And we have to ignore, so these are matrices order lambda squared. Okay, so we're going to ignore all matrices which are of order lambda squared. Now, if you take this one and plug it into here, let's do that. So the transpose of the identity is the same. Right? And this is going to be equal to eta. Now, what this is that, see, the 1 eta 1, okay, gives me eta. And then I have lambda transpose eta 1, which is lambda transpose eta. And then we have eta lambda, and then we have lambda transpose lambda, which we ignore because we are ignoring lambda squared terms. Excuse me. So we are ignoring that. So we can say that then this is nearly equal to eta because we are ignoring these terms. So the etas cancel from both sides, and we get lambda transpose eta plus eta lambda equal to 0, which is the same as eta. I'm not underlining, they're all matrices. Eta lambda transpose plus eta lambda is equal to 0, which means that this matrix eta lambda is antisymmetric, right? That's what it means when the transpose is a negative, then that means that this matrix is antisymmetric and therefore all the diagonal values of this matrix is 0. So what is it actually? So let me write it down. So what is this equation in terms of indices? Let's say AB, lambda, and lambda has up-down indices, so BC transpose plus eta AB lambda BC, that is equal to 0. And what is this? This is lambda AC plus lambda CA equal to 0, which means, of course, the same thing, that lambda AC is equal to minus lambda CA. Okay, that is exactly what antisymmetric means. So we have used the eta to lower the index of lambda, and once we do that, we find that the infinitesimal Lorentz transformation is described by the components of a tensor which is antisymmetric. And we know how many components there are of an antisymmetric tensor. So how many components are there? Can someone say?
6.
6. Who said that? Raj. Okay, good. Now, someone, maybe Raj or maybe someone else, can tell me as to what is the significance of these 6. So there are 6. Yeah, go ahead.
3 rotational and 3 boost.
Very good. Which means that there are 3 rotations. Which 3 are the rotations?
X, Y, Z axis.
Yeah, I realize that. Rotation means that. But see, the independent components here, what are the independent components?
Sir, lambda AB, where AB is not equal to 0. Those signify 0.
No. What I want is, can you be a little more specific in terms of spatial components? So if you have something antisymmetric, it's like FAB, right? FAB has exactly the same property. So we know that the independent components are like 0 alpha and lambda alpha beta, right? Now, which of these 6, so there are 3 here, alpha beta run from 1 to 3, and 3 here, that makes 6. So which of these 3 should be identified with the boosts and which 3 with the rotations?
So lambda 0 alpha should be represented by Lorentz boosts, and
So lambda 0 alpha you're saying, and so you would like to write this as what? As beta alpha, right? Where beta is V by C. And what about lambda alpha beta?
That rotations.
How do I relate it to, rotations are described by an axis and a rotation around.
Okay. Some eta alpha beta gamma and rotation about gamma.
Eta alpha beta gamma, what is that?
Means like if AB we connect it with a magnetic field by an eta alpha beta gamma, and
not eta. You mean the Levi-Civita, right?
what are you Greek letter?
That's not eta, right? That's epsilon. Epsilon alpha beta gamma. That's correct.
Sorry.
Then there is some vector, spatial vector, whose gamma is the direction of that vector, and there's some angle theta. That's what they are. So this is basically the way the lambda, the small lambda, which is the infinitesimal part of the capital lambda, that is how it decomposes, okay? So the decomposition is very clear. And we have this in terms of the angles. And you see there is another useful way of remembering this. See, this one is 3 components in space, but it's obviously 3 components of a polar vector because there's only one spatial index, whereas this, it's an antisymmetric tensor, so it's an axial vector. axial vector has to do with rotations, and the polar vector has to do with boosts. Okay, so these are our Lorentz infinitesimal parts of the Lorentz transmission. All right. Now let us uh, so from here, what we get is the following. So from sorry, this is xb. I forgot xb. So from here, you see this is the following. So the infinitesimal transformation will involve two indices because lambda has two indices. So there are two directions involved, right? And of course, one of them could be zero, the other could be space. I mean, this is the way we describe it. And so we want to write down this, and this is, so you see, it's a little different from the way we have been doing things. This one actually is this xb delta AC minus xc delta AB. Okay, now if you think about it, then you remember that when you do a delta of let's say by a vector angle theta of this, then this is something like theta cross x. You've derived such a formula when dealing with rotational motion in mechanics, right? Right? And so this, this is exactly in this form. If you look at any component, then that will be exactly in this form, except that we are dividing, this theta is not there, so it's the direction of theta which comes here. Okay. So that's exactly what it is. Delta BC XA is given by this. Now, when you look at fields, so we want to think of phi of x. That goes to phi tilde of x tilde. Well, phi of x tilde, because phi is the same as phi tilde, so it's a scalar. I'm talking about a scalar field. So what is this? This quantity is phi x plus lambda dot x. I mean, I'm sort of writing it in a condensed form. And when you do a Taylor expansion, this is phi of x plus, and I'm not going to derive it. So let this be a discussion. So what this is that, yeah, so from here, actually, I don't want to write this like this. What I want to do is notice that I can make a Taylor expansion in powers of lambda, and I retain only the first power of lambda. So from here, I can write delta BC. Excuse me, I have a phone call. Hang on for a second. শেখর ক্লাসে আছি, আমি ক্লাসের পরে ফোন করছি আপনাকে। Okay, so delta BC of phi, that is really what we are interested in. Because remember, when we talk about the Noether charge, we always look at infinitesimal transformations. So what is this equal to? Well, the first thing is that when you do a Taylor expansion, there's going to be a derivative, right, of phi corresponding to this term. And of course, in our derivation of the infinitesimal transformation, we always take the derivative with respect to lambda, and that is the exercise that I'm asking you to do. So you have to derive this, and what this is the following: xb delta c del c minus xc del b on phi. Okay, so this is for a scalar field. And of course, we know that a scalar field is a scalar, it doesn't change, and so that's the transformation property. Now, if you have, so this is for a scalar, I should write somewhere scalar. So if you have a vector field, on the other hand, a vector field AA, for that, I can, or you could put the A up if you want, just to. Okay. Yeah. So if now we want to calculate this, then there is a term which looks exactly like this. Okay. That looks exactly like this, which means that we will have something like AB delta AC. See, one simple way to remember this is that it has to be antisymmetric in BC because lambda is antisymmetric. And because of that antisymmetry, you can actually write this down very easily. There's nothing else it can be because it has to be antisymmetric and the rotation has to be proportional to the original vector. So this is the only form you can think up to sign. Up to a sign and up to an overall multiplicative factor, this is the only thing you can write down, okay? And the multiplicative factor, you see, does not matter because I can always absorb it into the definition of the parameter. So here we get something similar, minus AC delta AB. So that's one term, but this is not all, see. In fact, I'll have more to say, because there has to be something like this. And therefore, we get XB del C minus XC del B acting on AA. Okay, so there are two terms corresponding to the infinitesimal transformation of a vector field. Now, this term is exactly like that. Unfortunately, I don't have space. So, what I would like to tell you, and especially Raj, is that this particular transformation happens, right, because A is a Lorentz vector. So this property that has to do with the fact that if even if A was a constant Lorentz vector, this term would be there. This term will not be there. It's only there because A is also a field. So if A was just a constant Lorentz vector, this term would tell you how the component transform because they're exactly like the way X transforms. And this is what is sometimes referred to as spin. And this one is sometimes referred to as orbital, which is the same as what happens for the scalar field. So the orbital is shared by all fields, but the spin part depends on the particular field whose transformation you are considering. Now, to be precise though, this whole business of Lorentz transformations came out from quantum mechanics historically. Okay. And the concept of spin, okay, is not something we can discuss out of quantum mechanics at all. Spin does not have to do with space-time transformations. So what we do is we actually ignore this part when we talk about classical fields. We don't talk about the spin at all because this has no intrinsic meaning. This is something intrinsic to the field, something which is the field's own property, and this is really quantum mechanics which underlies this. So this term would be taken into account when we do quantum mechanics, relativistic quantum mechanics or quantum field theory. This is the part which we pay our attention to right now, this part or even this part, okay? So we focus on the orbital part of the Lorentz transformation. Yeah.
So how does the spin, electron spin is related to this spin? Means, is there any relation?
Yeah. See, that's the thing. I mean, we can't actually discuss spin within classical mechanics because the concept of spin is something intrinsic. It is intrinsically quantum. And although I have written a term like that, it is very hard to give physical meaning to this term, except in some sort of a geometrical way. So the physical meaning of the spin has to do with quantum mechanics. Okay. Now, again, if you ask me, how does then a field transform under Lorentz transformation? It's a quantum field. Then I shall, of course, have to tell you that there will be a part of the spin which transforms like this, and the electron, which you know is a fermion, has what is called spin half. Now, this transformation relates to the electromagnetic field, which has spin 1. Okay? And there are fields with higher and higher spins. But then spin I cannot discuss outside of quantum mechanics. Spin is something which is a property of quantum mechanics. So that is why we don't quite deal with this term anymore. We simply ignore it for the purpose of classical field theory. So for classical field theory, we only look at orbital Lorentz transformations. Now, once again, for a discussion of this, look at Landau-Lifshitz classical theory of fields. But I don't want to elaborate on this because for this, I really have to go into quantum mechanics, which I don't want to do right now. Is this clear? So, Raj, those books which you read may have something to do with quantum mechanics. Maybe they were books on field theory where they were discussing Lorentz transformations. And if so, it makes sense to talk about the spin of quantum fields. So if we, for instance, are looking at quantum electrodynamics, then this term will certainly be included in our discussion of Lorentz invariants. Is that clear, Raj?
Yes, sir. Actually, that book was on gravity. So I was just checking the.
Yeah, in the case of gravity, of
No,
course,
it's
you will
not
see spin
particularly.
2.
No, not particularly GR portion. I was just studying why a scalar or a vector field in special relativity doesn't give the fields which describe gravity. I was just studying that part.
Yeah. So again, when you do gravity, if you do quantum gravity, then you'll have to include this translation. On the other hand, if you do only classical gravity, then this part is fine. This part will be there for all fields. It's very simple. Okay? Very, very simple. Okay. So, and that
One
is,
more thing.
yeah.
Sir, we ignore the first part because
Yeah.
when we talk about, let's say, classical field theory, so we
Yeah.
can ignore it. How we can ignore it? Means, does it become
Well,
small?
what we say is we only consider orbital Lorentz transformations.
We just say it, but there is no constant. We cannot show it that it becomes small or negligible or
See, the
something.
point is, I have told you in the first class itself that classical field theory is an approximation, right? But we can't discuss quantum field theory because there are many things that you have to learn from a technical point of view. So it makes sense to begin with classical field theory and then go to quantum field theory. Now, as I said, in quantum field theory, which is a larger context, that is a larger perspective, of course you'll include the spin term. So there is no cheating going on here. But what I'm saying is, from the point of view of the classical Noether theorem and its applications, it is enough to consider just the orbital motion. And this is the orbital motion that you see in classical mechanics as well. In classical mechanics, there is no such thing as spin. Similarly, in classical field theory, we ignore the spin of fields because this is an intrinsic property. We write this down because we know from quantum mechanics that that's going to be the structure. But actually, it is not there in classical mechanics because we do not look at this intrinsic property under Lorentz transformations. Okay, so this is a little tricky because, but on the other hand, it's not tricky if you go back and think about a little bit about quantum mechanics because you know the following. So, in quantum mechanics, What you do is you write down in non-relativistic quantum mechanics, let us say, you write down an operator J, right, which is L plus S. Now J satisfies the usual Lie algebra, right? So J alpha, J beta, commutator. Now we are talking of quantum mechanics, so we are talking about commutators. I h bar epsilon alpha beta gamma j gamma. So what does it mean for L and S? Well, L and S also satisfy exactly the similar algebra. So I don't want to write it down, you can write it down yourself. But the interesting thing is L commutes with S. Isn't that true? So this S part is what I call spin angular momentum. And L part is what I call orbital. Now, this division is known to you, right? You've already studied quantum mechanics, and this property is also known to you. Hello, Akshay. Hello, Akshay.
Yes, sir. Yes, sir. Yes, sir.
You remember this, right? So,
Yes,
what we're
sir.
saying
And
is now.
S also commutes with momentum and position.
Exactly, because it has no connotation at all with space time.
Yes, yes, yes.
It is something intrinsic.
Yes, sir. Yes, sir.
This is precisely the point I'm trying to make. So, now, if you permit me to go back to classical field theory and discuss this Noether coupling. Okay, so the point is that we will use the transformation law, which I wrote down before. XB del C minus XC del V acting on phi. And similarly, if this was a vector field, it will be the same. Okay, which means that we are only dealing with this orbital part. We are ignoring the spin part. Okay, so the question then is, what is delta BC del A phi? Right, and that is, you know, that is del A delta BC phi, and that is then del A, right, XP, okay, del C phi minus XC del B phi. So this has two pieces. Well, this is two pieces. Let me just do it here. One, when the partial derivative will hit this guy, so we have beta AB del C phi, and similarly from the second term, beta AC del B phi. And the other term will be XB del C minus XC del B del A phi. Okay, so these are the two terms we shall have to contend with. And now, of course, actually we need not have worked it out. What we notice is that delta BC for Lagrange density, the Lagrange density must transform exactly like phi, it's a scalar field. So this is equal to XB del C minus XC del B on phi. But on L, I'm sorry, on L, because it's like a scalar field. Okay, but I want to write this as a total derivative because only then I know that it is going to be a symmetry of the action. So what it is a total derivative of? And here is another exercise. It is a total derivative of this quantity. XB Well, so this is an exercise to show that this is equal to this. But basically, you can guess that when you do this, del A xb, that is eta ab, and you can see that the two terms will cancel. So indeed, this is equal to this. But we have succeeded in writing down the Lagrange density, the infinitesimal Lorentz transmission of a Lagrange density as a total divergence, as a delay of something, something which looks like, which has an A index on top and B and C indices, antisymmetric indices in the bottom. Okay. So this is what it is, but then we also know that delta BC, so we play our game as before, right? So we know that this is del L, del phi, delta BC phi, plus del L, del A phi, delta BC, del A phi. Okay, and we proceed as always, namely, well, okay, so we interchange these, and we have. I'm not writing the full thing. I'm only going to write del A acting on everything. So we have del A, del L, del A phi, delta BC phi, plus equation of motion times delta BC phi. And since we're going to use the equation of motion to equate whatever we have here to here, we have written delta BCL in two different ways. That's our trick. We always do that. That's a Noether way. It's not our trick, it's Noether's trick. So using the equation of motion, what we get is del A of, right? Del L and delta BC phi we know is xb del C minus xc del B phi. And we have, from here, we get minus xb del AC minus xc delta AB চন্দ্র আমি একটু পরে ফোন করছি, ক্লাসে আছি। Right? And so that's the expression we have. And now what we're going to do is notice what is inside. So del A xb. Oh, I forgot a phi here. Sorry. Okay. Times del L del A phi del C phi minus delta AC. Oh, I'm sorry. I made a mistake. Oh, I'm so sorry. Here, there should not be a phi. Nobody noticed it also. It's L, right? So this is also not phi, but L. So this delta AC L minus XC del L del A phi del B phi minus delta AB L. Whole thing is equal to 0. So using the equation of motion, that's what we get. So the quantity under the square brackets is the conserved Noether current due to Lorentz transformations, space-time Lorentz transformations. Okay? So let's write that down, the next page. So we have del A, some quantity which we call JABC equal to 0, where we just copy from the previous page, JABC is equal to XB. Okay, now here it is. I'm sure some of you have noticed that we have this we have seen this before, haven't we? When dealing with translations, we found that the conserved quantity was this TAC, the energy momentum tensor. And what we find is that when we make an orbital Lorentz transformation, then we do get a conserved current. And the conserved current, you see, has this very nice structure. So this one tells you it is like, if you think of this as a momentum, then this is like the moment of the momentum. And that is what the conserved current ought to be, right? It's like angular momentum, if you wish. So we know that this is the energy momentum tensor. So that is the relativistic analog of angular momentum. Okay, and so let us see what happens. So if we want to plug this in here, right? We can assume that this energy momentum tensor del A TAB is equal to 0 using equations of motion which we have, right? So if you now look at this, what we have is, so del A J A, so 0 is equal to del A J A B C equal to, so let us take the derivative del A here. So there'll be one term which is eta AB TAC, right? And another term minus eta AC TAB. That's when the derivative hits the x's. But there'll be another term which is xb del A TAC minus xc del A TAB. And that is 0, but this is anyway 0, right? Using the equation of motion, that corresponds to translational invariance. So using translational invariance, what we get from here is TBC is equal to TCB. So that means that for the orbital part, okay, this current is conserved provided, so or the it is if and only if, so JABC is a conserved Noether current for Lorentz transformations if and only if TAB is equal to TBA. Okay, so we know that of course we can make TAB equal to TBA by using the ambiguity, okay, that is inherent in the definition of the energy momentum tensor. So this is not a great, very stringent requirement, but I remember that when we made use of the ambiguity to make the energy momentum tensor for electromagnetism symmetric, there was this question as to why we're doing it. And one of the reasons I said it has to do with the coupling to gravity, because gravity is always represented by a metric. And the other reason here is that, the energy moment, the Lorentz transmission current, the Noether current corresponding to Lorentz symmetry, is the conservation law is easy to prove only when you have this property. So for a conserved energy momentum tensor. So if there is translational invariance, and Lorentz symmetry, then we know that two things happen. The energy momentum tensor will have to be conserved and it will have to be symmetric. If it is symmetric, then it is guaranteed that the conserved Noether current, that the Noether current for Lorentz transformations will also be conserved. Okay? So that's part of the thing that I wanted to say today, but few more things here. For instance, the conserved Noether charge. Now, we call that M, and the definition is, as always, d cube x J0 AB. Okay? And so another exercise would be to show that phi with MAB exercise is equal to delta AB phi. Okay. Now, so this is in the Poisson bracket sense. This is the Poisson bracket. So an extension of this, so these will all come as exercises. Okay. We have defined the four momentum PA from the energy momentum tensor. So what we did not prove is this. 0, okay? And well, I'm wondering whether I should go on with this or not. Maybe not. Maybe I should. Maybe I should leave it for the quantum field theory course, because if I do too much, then there's a problem. Okay, so at least this part, I think you should be able to see as to why, we have we call this the Noether charge. So you see, the property here is that MAB also is antisymmetric. Which means that it also has 6 components. 6 independent components, right? In 4 dimensions. In 4-dimensional space-time, MAB has 6 independent components. So there are 6 independent Lorentz generators. Now, what are the physical... so we know that the Lorentz generator generating infinitesimal space-time translations is the 4 momentum. We've been over that. And that does not have any ambiguity. We've also proved that. The question, of course, the question is, what about this? These are 6 Lorentz generators. Physically, do they relate to anything interesting? What do they do? Well, if they are 6, then you know that they can be classified as M0 beta and M alpha beta. And these are nothing but the boost generators. So then they generate the Lorentz boosts. And this then will correspond to the rotation generators, or angular momentum, orbital angular momentum. So there are 3 of these and 3 of these, And of course, M alpha beta is epsilon alpha beta gamma, L gamma, where L is the standard vector angular momentum. We already know this, the duality and so on, right? So basically, this is what I had to say about Lorentz transformations at this point. You see, the Lorentz transformation is quite dependent on the energy momentum tensor. So it's really the orbital Lorentz current, the Noether current corresponding to Lorentz transformations, is constructed out of the energy momentum tensor, right? And it's like a moment of the energy momentum tensor. And therefore, the orbital part, the orbital conserved Noether charge also has to do with the four momentum generator, the four momentum which induces, which generates infinitesimal translations. And that's what we have here. So that's basically the boosts here and the rotation generator, the angular momentum coming here. But this is orbital angular momentum. I keep emphasizing this is orbital angular momentum. It's not spin angular momentum because that will not show up in classical field theory. Okay. Is there any question up until now? Well, I think this is basically what I want. I had some more things to share with you today. So one of the exercises would be to write down what JABC is for electrodynamics. But because we have done this for a general field, for a general scalar field, and we know how the vector potential transforms under orbital Lorentz transformations, everything will go through. So you can actually write down what JABC would be simply from, because it's a very simple expression, you know. If you know the electromagnetic energy momentum tensor, then you know exactly what this is going to be. Okay? So we have this property that yes, there is Lorentz invariance, there is orbital and spin Lorentz transformations, and for the purpose of classical field theory, we only deal with the orbital part. When we do deal with the quantum field theory, we'll take the spin part into account. And we will be talking about there. The spin part has to do with what are called irreducible representations of the Lorentz group. See, here we did not worry about anything intrinsic with respect to Lorentz transformations. So we will talk about the spin part, where we shall introduce the properties of the Lorentz group. Okay? And we shall try to construct, not this year, next year, we shall try to construct the irreducible representations of the Lorentz group. And those irreducible representations will be characterized by something we call but you'll have to wait for some time to see all that beauty. So far in our course on electrodynamics, we won't be using this to a great extent. However, we shall be using translations, space-time translations to a great extent. So is there a question now on any of this? So is there a question on any of this? Now, I find that maybe I should just, before I do something new, let me ask some of the people who have never spoken to. I know those of you, I know Raj, I know those of you who were there last year. I know Aditya from the quantum mechanics class. I also know Oritri from the quantum mechanics class. But Gaurav, for instance, Gaurav, can you, are you okay with whatever we've been doing? Is there any difficulty? Gaurav? Hello, Gaurav, are you there? He says no, sir. Is that to say that he's not there? গৌরব গৌরব সরকার কি নেই ওখানে? No problems. Oh, good. So everything is okay, right? So I'm happy about that. But I'm going to assign you these exercises for discussion for tomorrow. I'll send you the problem sheet. But it's very important that you do these problems, uh, you know, by yourself, and also talk. If you have difficulties, raise those difficulties. So Shrestha, do you follow everything? Is there any difficulty? Um,
No, sir, it's fine till now.
it's fine up till now. All right. Is it too easy? Would you say that it's too easy? Maybe I should speed up.
No, sir, it's something which I haven't learned before.
You haven't done this before. Okay, good. So what we're going to do is to sort of end this part and now move on to something quite different. So we are going to leave the discussion of symmetries and Noether currents and so on. Although we won't forget our energy momentum tensor, that's very important. So what we shall do the next time is discuss. So the next time we shall be discussing, should be starting with the solutions. Okay, so solution of Maxwell's equation for a particular source. We are only interested in the simplest possible source for an arbitrarily moving point charge. Now, I would like to make one thing very clear because that is sometimes a source of confusion, namely that this point charge, it's always a point charge which carries a mass, and therefore the point charge has a particular type of trajectory. You'll all agree that it's a time-like trajectory in space-time. So the curve that this point charge will follow, okay, so it will be some curve which in our standard way of describing relativistic particles, it will be something like this. Well, bad diagram. Let me try it again. It's such a challenge. Okay, so this is a time-like curve, right? And what we would like to see is this is, of course, a curve which, we have given. The curve is described by a 4-vector, which is a function of a parameter which changes continuously along the curve, and we have chosen this parameter to be proper time. Now, this is what I mean by arbitrary is that this function of tau is an arbitrary function. Okay, it could be any function, which means that obviously we are going to observe charges which are moving with acceleration. In fact, that's the most important part. Because you see, if you only consider charges which are moving without acceleration, then we know from our theory of Lorentz transformations that we can always go to a frame which is moving with the charge, because the charge is following a time-like trajectory, and the observer can always become a part of the time-like trajectory. And therefore, we can reduce any problem, okay, of steady currents to a problem of statics. In fact, that's one of the ways of motivating magnetostatics as a relativistic extension of electrostatics. And we have done that in class as well, although we did not do that in detail because this is a question of electrodynamics, and I'm not interested in stationary phenomena having to do with electrodynamics. But you know how to do that even from the full Maxwell equation. You can simply go to the time averaging over long time intervals and obtain the static field. So because magnetostatics is just ordinary electrostatics from another frame moving, another inertial frame, there is nothing new in it. On the other hand, when we talk about an arbitrarily moving point charge, we know that the observer cannot jump onto this trajectory. So the observer is somewhere here. There's another light cone for the observer. So somewhere here, sitting and observing this charge, right? So let me try to see if I can draw that diagram, that lovely diagram, which, so this is the observer, let us see, okay? And that's the charge, moving like that. Now, yeah, I should draw it correctly, but maybe I should draw this. So when you see something, when you see anything, you know that it's something that comes from the past, right? So this is coming from the past, some charge, which well, it could be like this, but you begin to see it only when it hits your light cone. Only when hits your light cone, you begin to see it, right? Because that's when suddenly, well, I've drawn a charge, the trajectory of the charge like this, but that's the thing. And I can also draw it when it comes from outside and enters a light cone, right? When it enters the light cone, you begin to see the charge. Before that, you don't see the charge. Okay, so, and of course, after it enters your light cone, so it should be the other way around. And, yeah, I'll draw this one. Anyway, I'll draw it next time. My drawing is not my best forte. So the point is that, so this is x bar of tau, and this is x, the space-time coordinates of the observer. So you see, this interval, x minus x bar of tau, that's an interval, right? For vector. And the square of that is the invariant interval. That must be light-like for me to see the charge. I don't see the charge otherwise. From this position, from where I am at this point of time, I don't see the charge until and unless this happens. Okay? That's what I call seeing in any way. When I see you at that instant, your position, your space-time position and my space-time position must be like-like. Do you realize that? Okay? And so that's a key point. So this is going to be a very important point in our discussion. On the other hand, x bar of tau, we could have several derivatives. So this, remember, dx bar d tau is nothing but so that's the forward velocity. And we have acceleration du d tau for acceleration. And we also, I think you did calculate explicitly to show that a squared is 0. So a, the acceleration 4 vector, is a space-like 4 vector. On the other hand, u satisfies u squared equal to c squared. So u is time-like. U is a time-like 4 vector. The acceleration vector is a space-like 4 vector. Right? All these things we know. We know the equation of motion for an arbitrarily moving point charge because, you see, we will not consider back reaction. So what we will talk about is the vector potential, the 4 vector potential as a solution due to an arbitrarily moving point charge. These are called the linear Vickers potentials. So we'll derive these linear Vickers potentials, and in doing so, I'll hope to give you a better picture for this. And okay, so we shall talk about solutions in that case, and we will see some strange things happening. For instance, we will see that the electromagnetic vector potential has two parts. Okay, one part which only relates to the velocity of the particle, and another part which relates both to the velocity and acceleration. So, if you set the acceleration to 0, then the second part is going to vanish, but the first part will remain. Okay. On the other hand, the first part, because it only depends on the velocity, if the acceleration vanished, you know that it should reduce to the Coulomb field. So that particular FAB should reduce to the Coulomb field, right? Because we know that if something is moving with a steady velocity, we can always go to another inertial frame in which that particle is at rest. So the electromagnetic field strength due to the particle at rest will just be the Coulomb electric field. I hope my statements are very clear, okay? But we are of course interested in the second part. The second part which relates to acceleration, because it is that part, see, which will lead to this phenomenon which we're all waiting for, known as radiation. So electromagnetic radiation has to do with the second part. And we shall argue why that part, asymptotically, as you move to very large spatial distances, that particular field will have a certain fall off which is slower than the Coulomb 1 over r squared fall off. It has to be, because if it didn't, then we could not see light from the sun, for instance. So electromagnetic radiation is the most exciting and the most, I should say, so what we're saying is that electromagnetic wave propagation we have discussed symmetries of classical field theory, and now we're going to discuss solutions of Maxwell's equation. That is what this course is all about. So the rest of the course will be about radiation. Okay? To begin with, we shall ignore any back reaction. What I mean by back reaction is that we shall only worry about fields which are generated by this arbitrary moving charge. Now, in principle, you see, there could be external fields. In principle, the fields which are generated by a point charge may also affect the motion of the charge itself. Now, we don't take that into account initially. If we have time in the course, depending on when the semester comes to an end, we shall be talking about the back reaction. We shall be talking about what is called radiation reaction. Very interesting physics comes in there. Okay? But first, we must talk about this solution of Maxwell's equation. Okay, so we set the stage for next class, and now it is time to say goodbye for today. So I will